Hello students. So in the last class we started with rectification of a curve, which basically means that calculating the arc length, and we worked out few examples. We also looked into several formulas, which some of which we are going to implement today, and we worked out one or two examples where we saw if we are given a curve, let's say y equals to fx, then in that case how we can calculate the arc length between 2 points x equals to a and x equals to b. So today we are going to do a few more examples, and today we will start with a parametric Cartesian form where we calculate the arc length. So let's start with our problem. So example 1. So here our problem is find the arc length or length of an arc, length of the arc. It's the same thing, arc length of the curve x equals to let's say t and y equals to t square from the point t is equals to 0 to t equals to 1. All right. So if we are already given the curve and we are also given the point where we need to do the integration, then we really don't need to draw the curve, because we are already provided enough information to perform that calculation of the arc length. So here we are given the curve as the given curve is x equals to t and y equals to t square. So from here we can write dx dt as 1 and dy dt as 2t. So therefore the required arc length, is integral t running from 0 to t running to 1, because that is the limit for the parameter, and then we know the formula is dx by dt whole square plus dy by dt whole square times dt. So here we have t running from 0 to 1, dx by dt is 1 plus dy by dt is 4t square dt, and now this has become our simple and integral calculus problem. So we know that from one of those formulas we can be able to write this integral into a nice formula here, and then we just substitute t is equals to 0 and t equals to 1, and that will give us the required answer. So I'll leave that task up to the students, because this from here it is pretty much straightforward. So this is how you calculate the arc length if we are given the Cartesian parametric Cartesian system. We can consider another example of similar sorts. So example let's say 2. So find the arc length of the curve, let's say x equals to cos t, so and y equals to sin t for t equals to 0 to t equals to 0 to t equals to 1. So here also, not only that we know this curve, we also have all the vital information to calculate the arc length. So here we have x equals to cos t and y equals to sin t. All right. So from here we can very easily calculate our dx dt, which is basically minus of sin t, and our dy dt would be simply cos t. And now we are supposed to calculate the arc length. So the required arc length is basically integral t running from 0 to 1, and then we have dx dt whole square plus dy dt, it is better if we put it in the bracket, times dt. So, this is integral t running from 0 to 1, dx dt whole square is sin square t, and dy dt whole square is cos square t. So, this one we can integrate, we do not have to put it off. So, sin square t plus cos square t is 1, and there is square root of 1 is 1 dt and t. So, basically we will have t at 1. So, 1. The square root of 1 can also be taken as minus 1, because we have a plus minus 1 as the square root of 1, but we cannot take minus here because length is a positive quantity. So, we cannot have minus 1. So, minus 1 does not make any sense. So, that is why we have taken only 1 as the square root of 1, all right, and therefore, we got the length as a positive number. So, this is how to say a small essence of mathematics, I would say, where you have to be a little bit cautious what you choose as a value for, and here is the one such example, that we cannot take the negative value, we always have to take the positive value. So, this is how we calculate the arc length of a curve which is given in parametric Cartesian system, and of course, the points are given. So, the calculation is fairly simple. Next type of formula is basically of polar coordinate type polar coordinate system. So, let us work out few examples based on the polar coordinate system. So, we will do we proceed in the following way. So, example let us say 3. So, rectify or calculate the arc length, whatever. So, rectify the curve x equals to a theta plus sin theta and y equals to a 1 minus cos theta. So, how do we do the rectification? So, this is our given curve, right. My figures are a little bit how to say upside down, mainly because I am not a good good painter in a way, or good at drawing. So, let us draw this curve. So, it looks something like this. Now, about the drawing of a polar of the polar coordinate curves or any Cartesian curves, that is a different chapter. So, you may have to look into a chapter called how to draw the a chapter on how to draw the curves. So, there are formulas or methods where you learn about how you can draw a curve, but that is not basically our concern here. So, here we are assuming that the reader is already familiar with the concepts of how to draw a curve. So, this is how our curve will look like. So, this is A and this point is A dash, all right. So, now we first have to guess the limit, because if we have equation of a curve given in terms of polar coordinate system, so the rectification formula involves the integration for theta equals to alpha to theta equals to beta. That means we need to identify these two values of theta, these two angles we need to identify, so that we can do the integration. So, here we will try to do the same thing. We will first try to identify the range for theta, that is from where to where it is varying, all right. So, as a point, let us say any point on this arc, as a point moves from one end A dash to other end A of the one arc, the parameter theta increases, basically increases from minus pi to plus pi, of course. So, it will increase from minus pi to plus pi, yes, and the parameter theta is 0 for the vertex O. All right. So, this is vertex O, that is here, and 0 is like 0, real number. All right. So, as the arc is symmetrical about OY, so the arc is, I did not draw the symmetric figure, but it is symmetrical. So, the arc is symmetrical along OY or about OY, whichever you prefer to use, about or along OY. The required arc length is basically our arc AO A dash, which is 2 times arc O A dash, right, or 2 times arc O A. So, any one of the arc, and then you multiply by 2, and that will give you the length of the whole arc. So, we can do the calculation for any one of the, let us say, sub arcs. All right. So, now we have x equals to a times theta plus sin theta. So, then in that case, if we are calculating the arc length for any one of these sub arcs, we can basically have theta running from 0 to pi. All right. So, theta a times theta plus sin theta, and we have y equals to theta a times 1 minus cos theta. So, from here we will have dx d theta equals to a times 1 plus cos theta, and dy d theta equals to a times minus cos theta. So, basically sin theta, isn't it? So, that is what we get doing the differentiation, and now we know our formula where we have to substitute all of these. So, the formula says that the required arc length, AO A dash equals to 2 times the arc length, let us say OA. So, then in that case it is 2 times integral from 0 to pi. So, theta is running from 0 to pi, square root of dx d theta from the formula, dy d theta times d theta. Now, this is 2 times integral theta running from 0 to pi, dx d theta is a square 1 minus what is that, a square 1 plus cos theta, yes, a square 1 plus cos theta whole square, and this one is a square sin square theta. So, if we if we calculate this whole thing, then it will turn out to be 2a theta running from 0 to pi cos theta by 2. This involves some very simple trigonometrical calculation, and I am pretty sure you can be able to do that. So, ultimately we will be able to obtain 2a cos theta by 2, and we have another 2 here. So, this will be 4a, and once we integrate this thing, so it will reduce to 1 by 2. So, there will be a 2 here, and cos theta by 2 will reduce to sin theta by 2 integral from 0 to pi. So, when theta is pi, then in that case this is sin pi by 2, and when theta is 0, then sin 0 is 0. So, 4a times 2, and then sin pi by 2 is 1. So, 1, that means 8a. So, that is the required arc length from here to here, although we calculated just from here to here by varying the theta from 0 to pi. So, this is one way where we can calculate the arc length whose how to say polar Cartesian polar representation is given. Although it is not entirely polar, it is actually parametric Cartesian representation, because the equations are given in x equals to phi theta and y equals to psi theta. So, instead of t they are using theta, and the limits for theta we are calculating basically just looking at the curve. So, it is not entirely a polar coordinate representation, it is actually a parametric Cartesian representation. So, this is one such example where we can use that formula. Now, let's actually work out an example where we will use polar coordinate system. So, let's go to another example. I don't know, 4. So, I lost the track, so it could be example 4. So, find the perimeter or arc length or rectify, they are all the same thing. So, find the arc length, or let us say perimeter. So, perimeter means actually the whole arc length in a way. So, the entire arc length. So, perimeter of the cardioid r equals to a times 1 minus cos theta. So, the solution. So, how to draw the cardioid, that is a different issue, and that is a different topic to be studied. So, I recommend to read some books where they have addressed this issue, that how you can draw a curve. Now, the cardioid will look something like this. This is our A, that is 0. All right. Now, this curve, so this curve is symmetrical around the initial line, OX, and therefore, the perimeter is double the length of, therefore, its perimeter is double the length of the arc lying above the initial line. So, we just calculate the arc length above the initial line and we multiply it by 2, and that will give us the perimeter or the entire arc length of the cardioid of the initial line. So, the given equation is r equals to theta times 1 minus cos theta. So, from here we can calculate our dr d theta, and dr d theta is a times sin theta. It is better to write some sentences. So, the given equation of the curve is this one, and then we do the differentiation. All right, and theta is basically varying from 0 to pi. So, 0 to pi to cover the entire arc length. Now, the required arc length is the required arc length or perimeter. So, let us use the term perimeter. So, the required perimeter equals to 2 times length of the upper arc, Now, the length of the upper arc will be calculated by theta running from 0 to pi square root of r square plus dr d theta whole square. This is where we are using the polar coordinate form for calculating the arc length. So, we have used that formula here, all right. Now, we substitute these two values. So, let us substitute the values. This will be r square. So, 2 times integral from 0 to pi, we will have a 1 minus. So, we will have a square 1 minus cos theta whole square plus a square sin theta whole square, that means sin square theta d theta. So, from here we will basically obtain 0 to 2 pi, from here we will basically obtain 2a sin theta by 2. This is a very simple trigonometrical calculation which I am leaving up to the students, d theta, and then this one will be 4a sin theta by 2. So, its integration will be minus 2 cos theta by 2 integral from 0 to pi by 2. So, this will be actually minus of 8a cos pi by 2 plus cos minus cos 0. So, cos pi by 2 is 0 and cos 0 is 1. So, this is basically 8a. So, that is the required arc length or the perimeter of this cardioid, this one here. So, here the given equation was actually in polar coordinate system, and using this equation we can be able to, so using this equation we were able to calculate this arc length here, and multiplied by 2, that is here, and that will give you the whole parameter. So, that is basically the required perimeter of the cardioid. So, we can work out another problem just to get more familiar with this topic actually. So, let me consider another example. So, another example. So, find the arc length of the curve given by cardioid r equals to a times 1 minus cos theta, and it is find the arc length of the curve given by cardioid, and it is divided by the line 4r cos theta 3a equals to 3a. So, this is the required, so the cardioid basically is divided by the line, this one here, and then the arc length, we have to calculate the arc length of I mean when this line is dividing the cardioid. So, if we draw this curve, so unless we draw this curve we will not be able to understand the problem. So, unless we draw this curve, so let us draw this curve. So, this is the curve. So, that is our origin. And this is, let us say, C, B, and that is basically theta equals to pi by 3. So, the given curve and the straight line are the given curve, and the straight line r equals to a times 1 plus cos theta and 4r cos theta equals to 3a respectively. So basically this is the line and this is the curve, and they intersect one another at B and C. So from here we can therefore the point of intersection can be calculated by substituting r equals to so from here we can substitute the value of r here, so that is 3 by 4 cos theta equals to a times 1 plus cos theta, and from here we will basically obtain a quadratic equation 4 cos square theta plus 4 cos theta minus 3, and if we solve this equation then we will basically obtain cos theta equals to half, and if cos theta is half then theta is pi by 3. So they are intersecting at the point theta equals to pi by 3, and we have to calculate the value of r here. So we can substitute for theta equals to pi by 3 here, that will give us the value of r, and another value of cos theta is ignored because the other value is cos theta equals to minus 3 by 2. We can write the other value cos theta equals to minus 3 by 2 is inadmissible. So we have ignored that value, and for theta equals to pi by 3 we can also calculate the value of r. So that's the point where they are intersecting one another, and the required arc length of the arc, let's say, so this is the arc for which we have to calculate the arc length. So the required arc length ABC, we have to write the correct order, so CAB. So CAB equals to 2 times arc length. What is the arc length? Then upper half, because it is symmetrical, so the arc length AB. So since it is symmetrical, we just write 2 times arc length AB. So this is basically 2 times integral theta running from 0 to pi by 3 r square dr d theta whole square times d theta. So we know that our r square is a square times 1 minus cos theta whole square, and dr d theta is very simple to calculate from here. So dr d theta is so here it is minus, so dr d theta is basically a sin theta. So this is a square sin square theta d theta, and if you do the simplification then we will basically obtain here 2 times theta running from 0 to pi by 3, we will obtain 2a times I believe sin theta by 2, and we basically do the integration like we did before, and then we'll get our required answer. So here we saw that we had to calculate the arc length of the curve given by the cardioid, and it is divided by the line. So that means that this part of the cardioid or this part of the arc length we needed to calculate. Since it is symmetrical, so we just calculate the one side and multiply it by 2. So that's what we are doing here, and here it's fairly just it's pretty much just a simple calculation like we did before, and that will give us the required arc length between these two curves. So I tried to cover enough examples from all of these type of coordinate system: Cartesian, parametric Cartesian and polar coordinate system, and we will continue with our next topic, which is basically surface integral, in our next class, and I will try to include some examples on rectification in our assignment sheet. and I look forward to you in your next class. Thank you.